Go. Welcome back. We're in session 2 of lesson 4. It's still Monday, the 3rd of February. It's from week 5. We just started talking about the concept of binary addition. We also started talking about overflow in our first session of this lesson. We're going to move on to the second session where we're going to introduce what we call signed integer representation. Today, I will be very happy if by the end of this session we finish signed magnitude representation and also 2's complement. We'll talk more about this in a bit. The signed magnitude is not for public use. I would actually say that this is more of a historical representation. It's not even in MATLAB. This one is used in MATLAB for what you might call the int 8 through int 64 data classes. And you might ask yourself, as I did myself, why would Jeff ever show us what signed magnitude is all about if it's not even relevant in the discussion of signed representation? I have 2 answers for this question that we'll get into soon. The major one of which, when we're choosing a data class, one of the major questions that we might ask ourselves are what are the strengths and weaknesses of our specific choice, and why do we implement those? I do want to be very explicit with you all in building a mental model of the different ways that we think about data class representation and how they relate to each other. We're going to continue to build nuance in this, but I want to create this chart, which I'm going to think of as the foundation of numeric data types. The bottom of this foundation, if we think about this as a pyramid, is what we're going to call unsigned integers. And we might say that every decision has what we call a theoretic basis. And then also we could call a practical basis. We're going to do our best to thread the needle between those. So theoretic is we have the data class, or I don't know what you call these, like radix representation. So you might call this a radix R representation. In this class so far, we've had R equal to 10, R equal to 2, and R equal to 16. We also talked about the idea of binary addition and radix conversion. What do I mean radix conversion? Yeah, we talked about the idea of going from binary to decimal and decimal to binary. And then also decimal to hex, hexadecimal, hexadecimal to decimal. All right. In the practical representation, to be honest with you, we talked a lot about this concept of what you might call computer architecture. So at the base level, every bit of syntax is electronic design, right? So you might call this, at the base level, computer architecture. From what subfield does computer architecture come? Say it again. Yeah, a computer architecture is a subfield of electrical engineering, and you might call these circuit design. And the reason that it's important to do this, or to be aware of this, is one of the first problems that was solved historically, and is in fact what you might call underpinning of the entire process of capturing numeric data class manipulation, is the idea that when we do binary addition, these things are actually created as physical circuits. At some point, I'll see if I can get you reference. In fact, maybe I can have a sponsor during lab today. Are we going to chat a little bit during lab today? Will you remember to remind me about Ben Eater? Yeah, I'm going to link I don't have a lot of, I could imagine spending 60 hours a week making YouTube videos and doing nothing else with my life. One of the things that I would do is I would teach you all how to design a 16-bit floating point computer from scratch. So we would buy breadboards, we would buy components, we would create the entire arithmetic logic unit, we would create a floating point unit, we would create a control unit, and we would actually breadboard a 16-bit binary computer so you could see under every addition what's happening with the electronic signal that you actually send when you write the addition sign, right? If I tried to do that now with my current job and current family, I think I would die and get a divorce. We won't do that. There's a man who used to work for Khan Academy called Ben Eater. He has a series of YouTube videos that go very deep into showing breadboard designs of circuits. I will upload that online. The reason that I want to talk about that in name, at least, is the ability to add two unsigned binary integers sets a foundation for the entire numeric manipulation process that happens at the very, very low level of your computer. Another way to say this is we studied now what we're going to call the theoretical underpinnings and the practical underpinnings of the entire set of data classes. Could you guess what, now that we know how to do unsigned integers, could you guess what next we're going to do? Signed integers. So we build our understanding of signed integers off of or on top of our understanding of unsigned integers. And then once we're thinking about unsigned integers, could you guess the two types of knowledge that we're going to be cognizant of as coders? Yep, theoretical. And then practical. It's almost like theory and experimentation, right? It's almost like science. In theoretical, we're going to talk about signed representation for these integers and the two representations. And we're going to have two of those. We're going to have one called signed magnitude. And then the other one is going to be called 2's complement. Two different approaches to encoding unsigned integers. Could you imagine what we're going to... So one of the things that we wanted to do theoretically when we were encoding and manipulating unsigned integers is to add them, right? Could you imagine what we also want to do for signed integers? Yeah. We have not talked about subtraction algorithms. That's not something that we talked about this quarter, and that's okay. Let me ask you this. As good mathematicians, if we've solved a problem once and we want to build a more complicated problem, could you guess what we might want to do? Map the solution to our harder problem back to an easier one. So one of the major practical questions is, can we use intuition from unsigned binary addition to help manipulate, this is not great, signed binary numbers. In particular, one of the major things that we saw, I mean, we haven't actually seen this in this class yet because I haven't actually built the freaking circuits, but every single one of these representations at the base is a sequence of voltages, right? And then to manipulate those voltages, I build further circuitry that allows me to send the voltages through and change them appropriately. In order to do binary addition, we have very complex circuits. They're actually not too bad, but it did take a few decades to figure these out well. Could you guess what one of the desires that we might have for figuring out how to manipulate signed integers? Yeah, turn the representation into a form that can be mapped back into the same type of manipulation that we do for adding and subtracting unsigned integers, right? So we'll come back to this in a bit. I'm not going to fill these top two layers out, but I do want to telegraph where we're going in this. So at the bottom of all the stuff that we're doing in terms of data classes, what sets the foundation for all data classes in this class? Unsigned integers. On top of that, we build signed integers. Then we're going to do this called fixed point numbers. And then on top of fixed point numbers, anybody know the pinnacle of numeric representations? Yep. In MATLAB and C and Python and Java, you know what these are called in MATLAB? Double and single integers. Sorry, double and single. These come from 1984 Institute of Electrical and Electronics Engineers. It's a very, very famous professional organization for people that design this stuff. There is a 1984 version of this thing, and there's also a 2008 version. Can you guess which one we might study if we were to study it formally? 2008 is the most recent one. All of this stuff, in fact, we'll talk more about that, comes from this. So like entire languages and architectures are based on this representation. MATLAB, the default data class in MATLAB. So if I just go back to my MATLAB and I say x equal 78. If I want to know the class, so let's clear, sorry. So let's do x equals 78. What's the default data class that MATLAB represents underneath? But if I'm going to understand doubles, this is an actual opinion that I have as a person that has read thousands of hours about teaching and learning. In order to really understand what's happening in doubles, we need to go back to the beginning. So lesson 3 was all about signed integers. Could you guess what, unsigned integers. What's lesson 4 all about? Yep. What's lesson 5 all about? Floating point. What about, fixed point. And then lesson 6 and 7. Yeah, so the funny thing is, we're going to call this, lesson 6 is we're going to call kids play. And then this is kind of funny. Adult play, which is always a fun thing to do, right? Yeah, we're going to go from, so in lesson 6, we're going to see what you might call the training wheels. We're going to look at floating point numbers in 8 and 16 bits. And then in lesson 7, we're going to look at floating point numbers in 32 and 64 bits, right? All of the entire process of which is to get you a deep understanding of what's happening when you encode numbers, numerical data, in your computers. Okay. Any questions about that? Probably a ton. Let's take a look at our first data representation. So this is going to be the sign magnitude representation of a signed integer. What is a signed integer? From what set do the signed integers come? Yep. Sine and cosine. That's funny. Okay, so we're going to say let y be equal to, or be an element of z. All right. Let's set y to be equal to the decimal number 91. Can you give me the corresponding binary representation of y? Well, it wouldn't be 64 plus 32, right? 64 plus 16. So let's see. Let's do an 8-bit. No 128s, 164, no 32s, for sure 116, right? And then 80 minus 91 minus 80 is 11. What's 11? Is 8 and 3, right? So that must be like 8, no 4s, 1, 2, and 1, 1. Could you imagine a very, very natural way, if you have 8 bits and you want to capture this thing right there, could you guess what we call that in terms of this number? The sign. What's another way to write the sign algebraically? What number would you raise -1 to get +1 in the power? Any ideas? Well, let's see. Let's think about this as B7, B6, B5, B4, B3, B2, B1, B0. To encapsulate the number 91, I don't actually need the most significant bit there, right? I just need the trailing bits, and then I can think about the value of the most significant bit as encoding the sign. So in particular, we could think like, okay, let's go ahead and think about this number as like -1 to the power B7, and then we'll multiply the entire thing by the bit string B6, B5, all the way B1, B0. Could you imagine what that bit string is in binary? So if I were to decompose this thing in a decimal representation, what would the value of that thing be? How do I write it as a sum is another way to write that. Yeah. -1 to the B7, sum from I goes from to 6 of B sub I times 2 to the power of I. This number, whatever this is, I don't want to call this the mantissa. Why don't we call it the magnitude? Why would I call that the magnitude? Yeah. If this is the magnitude, could you guess what this is? Yeah, direction is a geometric way to interpret that. It's the sign, it's an algebraic way to interpret that. That's awesome. God, you all are geniuses. If we were just a few decades older, we might all be rich, huh? Okay, so then we think to ourselves, every number y in z is given by its sign times its magnitude. Okay. Let's try y equal to negative 91. What's another way to say negative 91? Negative 1 times 91, which is negative 1 to the 1 times, yeah, I don't know. Should we be a little bit more strategic? What did I do there? Okay. Now, is that really true? Yeah. Under what we call the sign magnitude mapping. This for sure is not the unsigned int map, right? What value would this be for an unsigned int? Yeah, 128 plus 91, right? Because this bit right there would represent 128 times 1. Okay, so let me ask you this. For the signed integer representation, let's do the signed integer signed magnitude. And let's start with 8 bits. And let's say if it's stored as B7, B6, B5, B4, B3, B2, B1, B0, this right there is an assignment operator. This right here would be the bit string in memory. This right here would be the quote-unquote decimal interpretation of that bit string. What's the decimal interpretation of the 8-bit signed magnitude representation? each number has a sign bit. This thing right there we're going to call the sign bit. What are we going to call this thing? So what's the corresponding decimal representation of that thing? -1 to the sign bit, which means if the sign bit is 1, the sign is -1. If the sign bit is 0, the sign is positive. So 0 value represents positive numbers, 1 value represents negative numbers, and then we multiply the entire sign by the corresponding. Where do we get the interpretation of the magnitude? Upon what basis is this built? Unsigned integers. It's literally just stealing all those ideas and decrementing the number of bits by 1, right? Okay. So then claim. This now is a piecewise function. Anybody see a problem with this?
Max value is less.
For sure. Is there any way to solve that problem? Is there any way to get the max value equal to the max value of the other one and encode a sign? The moment we decide to encode a sign, what happens? We lose a bit, right? Kind of. We'll come back to that later. Okay, so for one thing, an immediate problem when we try to do signs is that we're losing the range of information that we can store. Any other problems? Yeah, say that again. Uh-oh. There's what we're going to have, positive 0. Give me a positive 0. And a negative 0, which would be 1, 0, 0, 0. Okay, so that's one thing. I guess we call this smiley face upside down 1. Any other smiley face, upside down smiley face, a frown, I mean? Something else that you see? How does addition and subtraction work? Well, what would happen, so let me ask you this. What are some of the things that we need to be conscious of if we're going to store negative and positive numbers and do additions with them? Yeah. What happens or subtract? I mean, they're actually doppelgangers of each other. Signed integers. So if I have an addition and I have a signed integer on this side and a signed integer on this side, and I say that the output z is equal, we need a way to check the sign of the output. So the moment that we need to check the sign of the output, what are we immediately going to need to do? We need to check the sign of x. We need to check the sign of y. If they're both positive, then we assign positive. If they're both negative, then we assign negative. You're just making sure I'm awake, right? That's awesome. Beautiful. Keep going. If they're both negative, we assign negative. But what if one of them's negative and one of them's positive? Then what do we need to do? Then we're going to check magnitudes, and then we're going to have this whole if-else condition, right? If x is positive and y is negative and magnitude of x, if the goal is to map the stuff that we do in signed integers back to the stuff that we do in unsigned integers, what have we just done to our design problem? Does solving this problem in any way relate to stuff that we solved in the unsigned integer problem? A little bit, in the sense that we have the magnitude is the same unsigned integers, but we're going to have to introduce an entire new circuitry that allows us to do checks, right? And in particular, we're going to have to make sure that all those circuits, all that stuff, goes into the decision just to assign a positive or negative. But what if the two numbers have equal magnitude? One of them is positive, one of them is negative, and they have equal magnitude. Which zero are we going to choose? So now all of a sudden we have all of this logic sitting on top of the signed representation that makes us do a ton of work before we actually do our addition. So we might ask ourselves, hey, this is all nice and great. Definitely we need a bit to encode the sign, but is there any possible way that instead of using the first bit just as a sign, that we can do some other representation and take advantage of all the work that we did to do unsigned addition? Okay. Could you guess what the answer to that question is? Note, sign magnitude does some good work. What's the major bit of good work that it does? Yeah, it stores the sign as a leading bit. But the sign magnitude also does what? Makes addition, subtraction, and zero complicated. And seemingly unrelated to unsigned addition. Let's pray, and by pray we mean sit in a room for about 15 years and think really deeply and make a bunch of mistakes for a better way. The better way that we're going to study is something called 2's complement. And then this is really only the second time I've taught this, so I'm going to break my rule. My rule is usually I want my students to intuit for themselves by building up the foundations step by step. I haven't figured out how to do that yet with 2's complement. So I'm going to actually give you the mechanism before we do this. So we're going to call this a 2's complement. representation of an 8-bit signed integer. What does it mean, 8-bit signed integer? Let's go ahead and write the string in terms of how we encode it. B7, B6, B5, okay. Could you guess what one thing we might want to maintain from sign magnitude? What was one of the really cool things about sign magnitude? The leading bit represents the sign. So we'll call that the sign bit. If B7 is 0, we call that a positive. If B7 is 1, we call that a negative. And then we had this claim that in addition to the sign bit, we're going to think about these back bits as representing 2 to the B6 times 2 to the 6, B5 times 2 to the 5, B4 times 2 to the 4, B3 times 2 to the 3, B2, B1, B0. So the claim of 2's complement is instead of thinking about this thing as the exponent on -1, what if we thought about this as scaling and shifting the entire number down. This is, I'm kind of letting this fall from the sky as if I was speaking to a numerical analysis god right here. So the claim on this is, what if we thought about that first bit? If it's 0, what happens? I don't even think I did that right. What happens if this is 0 in this representation? The -128 gets hit with 0, and then I'm literally left with the same magnitude as I did before, right? What if this is 1? So let's take a look at an example under this. What would y assignment operator 1, 0, 0, 0, 0, 0, 0, 0 represent? So this is assignment, not equality. And we'll think about this as a binary representation, but we're going to call this a 2's complement map. What do I mean 2's complement map? The most significant bit gets hit with what value? Yeah, so this is B7 times -128 plus sum I equals 0 to 6 B sub I times 2 to the I. What do you know about every single one of these bits? Bit 0 through bit 6. What value are they? They're all 0, right? So this is now just B7 times negative 128 plus 0, since in this exact example, B0 equals B1 equals B6 equals 0. But what was B7 in this case? 1. So what's the corresponding value of this particular unsigned integer? Negative 128. Now here's a question for you. Suppose for a minute I wanted to encode negative 127. What is negative 127? Well, it must be negative 128 plus 1. Well, what is that? 1 times negative 128 plus 1 times 2 to the 0, which is equivalent of saying 1 times negative 128 plus 0 times 2 to the 6 plus 0 times 2 to the 5 plus plus 1 times 2 to the 0. Well, what would that be in this 2's complement map? This is not an unsigned integer representation. This is what we call 2's complement representation. Okay. And we'll stop in 2 minutes. I want to do 2 more examples, and when we come back next time, we'll get a sense of this. All right. What about the number negative 1? Yeah. Negative 1 would be negative 128 plus $127, but that would be 1 times negative 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. Well, what's that? This is not the unsigned integer representation. This is what we call a 2's complement representation. Let's do 2 more, and we'll take a break, I promise. What about 0? What was one of the downsides of sign magnitude? Sign magnitude had 2 values of 0. How would you get 0 in unsigned integer? Just be all zeros, right? Could you guess? One advantage to 2's complement is what? Is what we call a unique 0. Let's do 1 more. We'll write 3 lines of code, and then we'll call a break, and then we'll come back and do some lab. I don't know. Should we do 91? Positive 91. Let's see. 91 we said was 64 plus 16 plus 8 plus 2 plus 1, right? Is it positive or negative? if my signed integer has a positive sign, what does that immediately mean about the leading bit? 0. And the trailing bits in that case actually encode the magnitude of the positive number identically. If this thing has a negative sign, what happens? We shift the magnitude down by -128, which means that we're storing the complement of the bit string, which we'll talk about next time. The reason that I wanted to show you this is, one, so you can start to get a sense of some interesting maps going on, but check this out. We had this concept in MATLAB that we were looking at uint integers, right? Could you guess what happens when you delete the u? It becomes a signed integer. Hexadecimal, what does 8 look like? 1, 0, 0, 0, 0, 0, 0, 0. What did that line of code just tell you? We'll try another one. How does MATLAB encode signed integers? Two's complement. MATLAB's chosen data mapping for signed integers is two's complement. We'll learn more about two's complement the next time we come together. The point of this, however, is unsigned integer representation sets a base. We build on top of that sign, and then everything we do that is some manipulation of unsigned integers to account for other types of data that we might want to capture. Right now it is 12:06. I'd like to start talking again at 12:16. I have some updates about Lab 3, and then I plan to give you some time to read and think about Lab 3 today. So I will shut up during Lab. I'll see you in just a few minutes.